Hello, and thanks for using TickBoom. For this question, we're looking at B part 1, which asks, in how many different ways can R students be placed in 3 different rooms so that there is at least one person in each room? So this is a classic combinatorial mathematics question, but what we'll see is it's possible to tackle this without using any of the NPR or NCR techniques. We can just work this through with first principles. So if we start by just noting down the facts that we're dealing with, we've got R students into 3 rooms with no empty rooms is our constraint. And it's that constraint that makes this a little bit harder than your typical question. But the first thing to note is that we are dealing with students or people, so we can treat those as distinct. People typically aren't identical. And we've got 3 different rooms. So the generic way to frame this would be R items into 3 urns or buckets. That's a typical generic way to think about this. I'm taking a certain number of things and putting them into a certain number of other things. I think the best way to start tackling this is to think about what the answer would be if you didn't have this constraint. So if we were dealing with 3 rooms, room 1, room 2, room 3, and we just had to put our R students into those rooms without any constraint, the number of ways to do that would be equal to 3 to the power of R. Or in other words, the number of rooms to the power of the number of students. And to help flesh that out, to explain why that's true, if I've got no constraint, then I'd essentially just work through one student at a time and place them into one of the rooms at random. So student number 1 could be placed in 3 ways, because I'd just be picking any of the 3 rooms. Student number 2 could be placed in 3 ways, all the way up to student number R being placed in 3 ways. So in essence, we get 3 times 3 times 3, all the way up to R times. So we're doing 3 times 3 times 3 R times, which is 3 to the power of R. So that's what it would look like with no constraint, but we do have this constraint. So what we can do, well, there's a few ways to tackle this, but I think the easiest way to tackle it is to say, what is the total number of ways we could do it with no constraint, and then subtract from that all the number of ways that don't meet our constraint or are not the way we want to do it. So if we want no empty rooms, that's the same as saying that we don't want, or it's not only room 1 and 2. And it's not only room 2 and 3. And it's not only room 1 and 3, obviously. Because if that is what we were doing, then we wouldn't be satisfying this constraint. Now, if I draw up a Venn diagram, it might help to visualize what that looks like. If this box represents the total number of ways with no constraint, and if I just label these different options A, B, and C, so I could draw those circles A, B, and C, we essentially want what I'm shading here, which is the number of ways to fill the R students into the 3 rooms without doing A, B, and C, without dropping off a room. Now there's also the intersections that we have to think about, because we don't want to be doing any double counting here. So when I go only room 1 and 2 and only room 2 and 3, we see that only room 2 would intersect those. And if I do only room 2 and 3 and only room 1 and 3, so the intersection of B and C, only room 3 would satisfy those, and then only room 1 as well. So what we need to do is, when we're working out the number of ways each of these can be done and subtracting them, we also need to subtract from that only room 1, only room 2, and only room 3. And that's to help with ensuring there's no double counting. So if we can just work out the number of ways for each of these ingredients, we can then solve this problem quite easily. And actually we can come back to our generic technique here where there's no constraint, because if I'm looking at only room 1 and 2, that's equal to 2 to the power of r, because I'm essentially getting my r students into 2 rooms with no constraint. Same deal with only room 2 and 3, that's equal to 2 to the power of r. And same deal with only room 1 and 3. Each of those, we're just putting r students into 2 rooms. And when I'm looking at only room 1, only room 2, and only room 3, same technique, but it's 1 to the power of r for each of those, because we're putting r students into 1 room. There's only one way you can do that. 1 to the power of anything is 1, so that's easy enough. So now, where we get to is the number of ways to put r students into 3 rooms with no empty rooms is equal to the number of ways with no constraint, 3 to the power of r, minus these 3 ways that we need to exclude. So 2 to the r plus 2 to the r plus 2 to the r, those 3 different ways. But subtracting from that, so stopping our double counting, the only room 1, only room 2, only room 3. So minus the 1, minus the 1, minus the 1. We can simplify that a little, which gives us 3 to the power of r minus 3 times 2 to the power of r plus 3, because it's minus of the minus 3. And that there is the answer. That's how you can, well, that is the solution to this question. And then if you wanted to kind of check it, you could say, what if r is equal to 3? It's worth noting for this question, if you're going to have this constraint of no empty rooms, you need at least 3 students. Because if you had only 1 student or only 2 students, you wouldn't be satisfying this constraint. So we have to start from r equals 3. If that was the case, the number of ways would be 3 to the power of 3 minus 3 times 2 to the power of 3 plus 3. I'll just get my calculator and we'll put that in. 3 to the power of 3 is equal to 27 minus 3 times 2 to the power of 3 is equal to 8 plus 3, which equals 27 minus 3 times 8 plus 3 is equal to 6. And with a number that small, you could probably draw out all the ways just to test what you're doing. And you could then say, what does this look like if r is equal to 4 or 5 or any number you like, and this solution should give you the answer. So hopefully you found that helpful. If you encountered this question on an exam, I think the challenge would be not to jump straight to things like, NCR or NPR and trying to work out, am I dealing with combinations or permutations? The challenge with this question is actually that you can solve it with very simple techniques. You have to basically go back to first principles, and that's where maybe not every student would be able to have the calmness or clarity to do that. And again, in exam time, the key to success here comes down to practice. If you've practiced enough of these questions, then maybe you'll give yourself the best chance of knowing what to do and being able to step back and just think calmly about it and methodically and just work it out using logic, basically. So hopefully you found that helpful, and tick boom.